Thank you for coming. We're nearly at the end of the conference. 90 minutes of me, and you're free to go. Right? Is there anyone here who, well, put your hands up if you have learned something useful at this conference that you feel you can take back to what you're going to do. Okay, those of you who didn't put your hands up, then how can we fix that in this session? Why are you here? Right? What can I tell you in the next 90 minutes that will change your response to that? Anything. Fantastic. Right. Let's go. So I'm going to talk about complexity, which is something I'm going to claim I have quite a lot of experience of dealing with, but I suspect that's also something you could all say as well. It's something that afflicts most of us in the end. My name is Robert Smallshire. I work for and part own a company called 60 North, based in Norway. It's called 60 North because, well, it's at 60 North, almost exactly. That's where I live. And my career, which is plotted on this map, essentially started about 100 miles north of here, and then has moved monotonically northwards with respect to latitude until I've ended up in Norway at 60 North. I'm not really sure what happens next. The Arctic, I guess. I already live further north than about 99.99% of the world's population, and there really isn't much else further north of where I live. But if I do go far enough north in Norway, I stop paying income tax, which is quite a good incentive. So, complexity, right? This is something you're all familiar with. It's obviously something you're all interested with, which is why you've come to this talk. And I think ultimately we are, what this talk is about is the fact that we are ultimately engineers of our own demise. You know, we do things like having 500 wires that are all the same color, right? I mean, why would you ever do that with no labels? How can anybody ever make sense of this? And I think many of us at times feel that the insides of our software systems feel or look very much like this, although there are certainly occasions where that's true. And we'd like to get into a situation where they don't look like this. But inevitably, we move towards this kind of situation. So in this talk, I'm going to explore some of the reasons for that. We're going to talk about whether it's inevitable or not. And the only thing that we can, perhaps the only thing we can affect is the kind of decay constant here. We can only ever defer it. Can we ever prevent it? And we're going to talk about what complexity is and what it means. So I'll start by, well, the talk is structured into 3 sections. I'm going to start by characterizing complexity, really a section on measuring complexity or different types of complexity that we can observe in real-world software systems. Then we're going to spend some time looking at the causes of complexity. Why does it always turn bad eventually? Does it always turn bad eventually? And then finally, I'm just going to suggest some tools for trying to control complexity. And actually, a very large part of what people talk about at any software conference these days is really, allegedly, about controlling complexity. A lot of agile engineering practices, if I can use the word engineering. Is Tom in the room? No. Right, I can safely use the word engineering without fear of having my talk derailed by Tom. So it's happened before to me, so I'm familiar with this. It's important to understand the techniques, some of the techniques that we can use for controlling complexity. I'm not going to really talk about agile techniques. I'm going to talk more about engineering techniques, perhaps. So that's my thing. Okay. Simplicity and complexity. Who here uses a programming language that has built-in advice about complexity into the runtime system? None of you. Well, you're all using the wrong language, possibly. So this is what happens when you fire up Python and type import this into the read eval print loop. And this isn't me advocating Python, although there are circumstances where I would do that. I just wanted to look at this poem that is printed out. It's Zen poetry called the Zen of Python that's printed out when you type import this. And this is called the Zen of Python. And specifically, I wanted to look at the first part of the poem, which is almost worth reading to you, I think. So beautiful is better than ugly. I think that's something that most of us would agree with. Explicit is better than implicit, which which is obviously a point about readability, I think. Simple is better than complex. Who can argue with that? Complex is better than complicated. What does that even mean? That's quite cryptic, isn't it? Flat is better than nested, sparse is better than dense, and readability counts. So there's one cryptic statement in the middle of this poem, which I think is worth unpacking a little bit and to find out what's in there and why this poem is drawing a distinction between these words complex and complicated, which by and large we use as synonyms in everyday speech. So let's look at the dictionary definitions. So complicated or complicate is about making things difficult, confused, intricate. It also covers the synonym with complex, but we'll ignore that for the conveniences of my argument. An involved, in complication, an involved or confused condition or state. Who has ever felt that at work? Come on, yes, you all have. So complication is something that we suffer from. Complex, on the other hand, has lots of different meanings. If I go to the IBM campus somewhere, right, that is a complex of buildings, right? It might be complicated. It might also be complicated in the previous sense, but the word complex there means something quite different. It probably means there's more than one building, right? And they're connected together or grouped together in one way. It's actually a statement about modularity, complex. Chemical complexes, really a synonym for chemical compounds. Again, modular things made of atoms combined in ways. Systems made of parts, right? And generally speaking, systems made of parts is something we value rather than, as opposed to monolithic systems, which is what we all too often build. So complex is a complicated word. It has lots of different meanings. And I think in the Zen of Python, my interpretation, it's Zen, so I think I'm allowed my own interpretation. My interpretation is that the complex rather than complicated is really saying build things that are complexes. Build things out of pieces which you can compose together to solve the problem you're solving, rather than making complicated, intricate things. That said, this talk is called Confronting Complexity. Arguably, I should have called it Confronting Complicatedness. Another word has entered or re-entered the lexicon of late, thanks to Rich Hickey, the man behind Closure, and several other wonderful things. He's trying to reintroduce the word complect, which is an archaic English word, which means to interweave or interconnect or plait, in fact, as you would your hair. I think he's going to have an uphill battle introducing this word back into the language. I've only ever heard 2 people use it, and one of them was Rich Hickey. So I think he's got quite a way to go. But if you do hear this word, then you'll know that it essentially is in my mind, it means complicated. So I'm not sure why he feels the need for the additional word. So let's move on and look at different ways of characterizing complexity and how we can measure it. And I've broken this first section of the talk up into 3 subsections. I'm going to look at control flow complexity, which is really complexity at the code or the statement level in an imperative program anyway. I'm sure you're all still writing imperative programs, right? Functional programming isn't really that popular yet, is it? Anyone doing actual functional programming every day? 1 person, fantastic. Good luck. And then I'm going to talk about structural complexity of programs, which is really how the pieces of a complex system fit together. And then I'm going to look at evolving complexity. I've spent time working in some pretty substantial systems and looked at them over long periods of time. I actually came into those systems quite late in their history, but very diligent source control practices over long periods of time, give you a wealth of data. And it's very interesting to look at how systems evolve over the long term, and you can extrapolate that forward and make some estimates, some models essentially of where you're likely to end up. Now, this section is about metrics, and we have to be careful with metrics. And metrics are often criticized because we tend to measure things that are easy to measure rather than necessarily the right things. That said, I think it's true that measuring something, as long as you're careful in how you interpret what you're measuring, can be a valuable thing to do. And if you look at Bill Gates' quote here, measuring programming progress by lines of code is like measuring aircraft building progress by weight. I mean, this is really a statement about what code is. Is it an asset or a liability? Right? And we tend to treat code as an asset, whereas really, often I think it should be sitting on the other side of the ledger. We should be trying to solve problems with the simplest systems that will solve the problem, not the most interesting system that will solve the problem, which is nearly always what we actually do. And simple doesn't mean simplistic either, when we're talking about the meaning of words. So control flow. Who here knows what a control flow graph is? Okay, 4 or 5 people in the room. So control flow graph is essentially a graph in the sense of the data structure. This is really hard to see on this projector, I'm sorry. It's a graph in the sense of a data structure of how control flow moves through your program as it's executing from statement to statement, is an easy way to think about it. And control flow graphs isn't a way we normally think about our programs. Normally they crop up in the context of building a compiler at the point there where you generate the code and you want to glue all your bits of generated code together in the right order so that they work and branch between them. And in fact, getting hold of the control flow graph from a program that you have in Java or C# or whatever is quite a hard thing to do. I don't really know of any tools that will spit out the control flow graph for a program as a data structure that you could import into a tool for dealing with graphs. So I wrote a compiler to generate my control flow graphs. For the language I wrote the compiler for is not significant to this talk, but it just means I had a way of generating some really nice control flow graphs. And this is really hard to see, but you can see in the graph there are lots of separate connected components in the graph, isolated islands of nodes which are connected together, and each one of these is a separate function in the program. And then we see the control flow within each function. And so you can see this function here, there's a very long list of statements with no branching, and then eventually we get into this horrific mess up here where there's branches and if statements all over the place. The reason this is so awful, right, is that this is a dialect of BASIC, right, with go-tos in it, right? And I think a modern control flow graph would not look like this. It's also a program that was deliberately obfuscated using go-tos. It's actually a textual adventure game from the mid-80s that was written in BASIC and then deliberately obfuscated to stop people figuring out how to solve the adventure. So it probably has some of the more interesting control flow graphs in the world out there. So typical control flow graphs aren't this complex, but we can, if we take a function in the control flow graph, very long function in this case, you can see essentially how control flow enters at the top and it can flow through the program in different ways. Each yellow box here is what's called the basic block in the program. There are no branches within each basic block. And as we exit each basic block, typically we're branching into one or more, or at least 2 other basic blocks. As you look carefully here, as we fly past, you might see some loops coming up quite soon. There's a go-to coming in here. We have a repeat loop until, goes back, up, around. Most of the things in the blocks are just statements or assignment. Another repeat loop here, where does that one end? Until, goes back around there. So control flow graphs are very interesting data structures, and in fact in this phase of the compiler I was writing the control flow graph is there to glue these basic blocks together in the most efficient way to minimize the number of jumps in the resulting code when you compile it down to .NET CLR bytecode, right? Because writing compilers for languages from the mid-1980s for the .NET CLR is something I do for fun, right? Because you can. But the control flow graph is interesting because it's an abstraction from the code we write. It's something we can generate from the code we write. It's something all of our compilers will generate from the code we write, but we never see it. But it tells us something about by analyzing the complexity of the graph, we can make some statements about the complexity of the program. And like all good things in computing, this was done back in the 70s, in this case 1976. I feel all of my talks are just a retelling of stuff from the 70s. That's just really how it is. And, well, who here is familiar with FizzBuzz? Oh, enough of us to play it. Great. I'm not going to make you play it. So FizzBuzz, for those of you who aren't familiar with it, is a very simple program or idea which is primarily used for interviewing programmers in screening interviews to work out whether they can write really simple programs. And that's its main purpose. And essentially the idea is that in the game you go around the room and each person shouts out a number. So 1, 2, 3, 4, 5, 6, 7 as we go around the room. But if the number is divisible by 3, you have to shout fizz instead of the number. If it's divisible by 5, you have to shout buzz instead of the number. And if it's divisible by 3 and 5, you have to shout fizzbuzz. Right? So when you get to 15 and 30, you shout fizzbuzz. Very simple. So this is a simple Python implementation of a fizzbuzz function, which when given a number, prints out fizzbuzz, or the number. Simple. And the reason it's a hiring, screening thing is if you can't write this program, then you shouldn't hire people. You can't do that. Sounds crazy, but it's apparently quite effective. What's worrying is it's effective because presumably there are people who get into the interview process who cannot solve this problem. So what we can do is we can look at the control flow graph of FizzBuzz, which is a very simple one. We start at the beginning with an assignment. Then we go into an if here. You can all read Python. This is the great thing about Python is anybody can read it. So we go into an if where we either go into the if block or we skip over the if block. Then we get to another if and we go into the if block or we skip over it to a print at the end. It's a very simple control flow graph. And what Thomas McCabe in 1976 said, well, was that if we count up the different interesting entities in this graph, the nodes and the edges, connectors in the graph, then they can tell us something about the complexity of the program. It wasn't quite that simple, unfortunately, because he also said, well, you have to account for the number of places you could return from the function. So in Python, there's an implicit return at the end of the function, so I've put it in here. That counts as an extra statement and an extra node. We have to count the return nodes specially as p. So we have 8 edges, 1, 2, 3, 4, 5, 6, 7, 8. We have 7 nodes in total, 1, 2, 3, 4, 5, 6, 7, and we have 1 return node at the end. Right? Everybody with me? Great. And then he had this really simple formula. Like many things in graph theory, it's fundamentally very simple. And he said, well, if you take the number of edges and you subtract the number of nodes and you add 2 times the number of return points, you get a number. So we can do the math and we end up with 3. Right? And he's, you know, he was one of these people who named numbers after himself, right? So he was Thomas McCabe, so this is the M number, right? This is the way to immortalize yourself. And so M is a measure of the control flow complexity of this function, and it's a small, simple function, and we get a number 3. We get a small number. M is 3. And what's interesting about this number is that it's a lower bound on the number of tests you need to fully test this function. Right? If you think about how many unit tests you might need to write to test FizzBuzz, it's at least 3, right? Because we know the function can do 4 things. It can print fizz, it can print buzz, it can print FizzBuzz, and it can print a number. Right? So we are going to want to test at least those 4 situations with our unit tests. And you know, we can go ahead and write some tests that test multiple of 3, multiple of 5, multiple of 3 and 5, and multiple of neither 3 nor 5. Right? So that's 4 tests. 4 is greater than 3. 3 is the lower bound on the number of tests. So this is an interesting statistic in today's world, I mean, he was doing this well before unit testing was really thought of or practiced widely, at least. But it's a lower bound on the number of tests we need. So even for these short functions, because the complexity is high compared to the length of the function, we need 4 tests, or at least 3 tests. And it's very rare in my experience that the number of tests you need is actually this number. It's nearly always at least 1 or 2 larger than that number. Okay, I just want to take a brief digression into readability as well, because complexity of that kind, control flow complexity, is of course related to readability. We all have experiences of writing really long, complicated functions with 15 if statements. We've all been the person who added the extra if statement to that function without refactoring or extracting another function. And if we listen to Uncle Bob, who invented all the things that were invented just after the 1970s in software engineering, he says the first rule of functions is that they should be small. The second rule of functions is that they should be smaller than that, right? So really, really small functions. Okay, so if you look at the kind of clean code approaches that Uncle Bob is advocating, he's saying, well, your function should never be more than 5 lines long. And anyone who's tried to do that knows that it's really difficult to do that, but you need a lot of discipline to do that. But the advantage of doing that is you cannot fit much complexity into 5 lines, and so it's very easy to test those things. And so, of course, the whole TDD approach drives you to build functionality in small, testable pieces like this. I put this one in because it's a counter-argument to Uncle Bob. I went to a wonderful talk by a lady called Kristin Gorman, who lives quite near where I live in Norway, at Java Zone a couple of years ago. And I'll read the quote for the people who can't read it at the back. And she said, "We insist on chopping everything up into such tiny fragments that all we end up talking about in our conferences is how we attach it all back together again." And I think that's very true as well. And she was making the point that if you're new to this code and you come into it, it can be very hard to understand what's going on because you can't read it like a narrative, right? She was saying that she wants to come into code that has not huge functions but longer functions that she can read like a story. Yeah, now, Uncle Bob will also make the analogy with a story, and he will say, well, it should be like a newspaper article, right? The first 5 lines tell you everything about the story you need to know, and you can stop reading. But if you want to know more, you can drill down a level and drill down another level, and you end up reading a 1,000-word article in the newspaper. But you don't have to read to the very end of a 1,000-word article to get the main point of the story. You can read the first function or maybe just a few levels down. And I think she had it was just a lightning talk she gave, but it was a very interesting argument. So I got hold of Kristin's code and Uncle Bob's code. She actually rewrote Uncle Bob's code from clean code in her style. And I know you can't read it here. But the interesting point is her code is also very simple. There's one if statement here. There's another if statement hidden here, which just bails out right at the beginning. But her code is longer, but it's also very simple and relatively easy to test for that reason. You need relatively few tests to do both of these things. So I think it's significant that low complexity is perhaps what people are wanting rather than shortness, right? I think it's fine to have a longer function if it has very simple control flow graph through it. So as I mentioned, I've worked with some fairly substantial code bases over the years. Every blue dot on this chart, which has been substantially truncated, if this chart extended as far as the data, it'd probably be into Russell Square, because it would, because some of the functions were just enormous. But what we have here is the size of function in lines of code, so 0 lines of code here. This is a 400-line function here. In this code base, they were up to several thousand lines of code. Jules May down the front here was telling me about functions the other day that were how long? 35,000 lines of code. Never worked with scientists.
It was translated from Portugal.
Okay. That's still not okay, though, is it? So this is the size of a function. and this is the complexity of the function. You can see there is arguably a linear relationship between these things with quite a lot of spread on it. And this is a data set from a single program with 98,000 functions in it, right? Which sounds like a lot. That's about 2 million lines of code. And I'm sure there are people here who are working with systems of in the million lines of code range. That's not uncommon these days. I mean, I think a million lines of code is that a medium-sized system these days? It's not a large system, I don't think. So there is certainly down here, there's a lot of spread out here, and I think a lot of these things end up being generated functions, frankly. They don't do very much, but there's a nice relationship down here. But what's interesting, I will make the numbers bigger on these axes if I do this talk again, but at 400 lines of code, we have a complexity of 80, right? So that's a ratio of about 5 to 1, right? So earlier I was telling you that the complexity is the lower bound for the number of tests you need. So over here, one of these blue dots needs at least 80 unit tests to fully exercise all the code paths through it. Right? Nobody wants to write 80 tests for a function. That's a single function. I think it would be extremely difficult to ensure that you had written the right 80 tests for a function that big. Very, very difficult. So we have a ratio of 5 to 1 in lines of code to cyclomatic complexity in this code base. I've done similar analyses on other code bases. You can do the same in code on GitHub these days. GitHub is wonderful for doing these kind of statistics because there's mountains of code, lots of which is quite good code, actually. And you can download that stuff and do these kind of things. And these numbers are not atypical, right? You know, the ratio might be 4 to 1 or 6 to 1 in a code base, but it's not 10 to 1 or 1 to 1. So 5 to 1, I think, is a fairly typical number. So think about what that means. That essentially means that every 5th line of code is a conditional. And that sounds about right. You're writing production code every 5 lines. You have an if statement, right? And if your functions are 5 lines long, they only have one if statement in them. That sounds okay. That sounds plausible, doesn't it? So then think about what that means. That means every time you write 5 lines of production code, you need to write another unit test. 5 lines isn't very much production code. You know, so when you think of it in those terms, because that's what this data is telling you, it's telling you that there's a ratio of 5 to 1 of cyclomatic complexity to production code. Every additional cyclomatic complexity point needs another test to cover it, at least one other test. So for every 5 lines of code, you need one more test, which is, I think, an interesting conclusion. We tend not to think about that ratio in that way. Certainly I don't. And perhaps if you're doing really rigorous, good TDD, that makes sense. And I think that's probably the kind of ratio you would end up with. But I don't think most of us are doing that yet. And it's a kind of scary number, right? Because you can't do very much in 5 lines of code. Well, you can make one decision, right? That's what we've just said. But, of course, there is a lot of scatter in this graph. It's not a beautiful linear relationship. So we can come up with a slightly more nuanced metric, which is called complexity density. So we have functions below this average line, which are longer but relatively simple. And we have functions above the line, which are shorter and relatively more complicated. Right? So we can have this notion of complexity density, which is it's essentially how many if statements have you crammed into certain lines of code. If every line is an if statement, you have a very high complexity density. If you've got one if statement every 100 lines of code, you have a very low complexity density. And of course, when I say if statement, you know, it could be a switch or whatever branching constructs you have in your language. I'm using if statements as a proxy for just branch in the control flow graph. So complexity density is an interesting number to look at, and it's nice because you can map it. It's a statistic that you can aggregate over any size chunk of code. So you can measure it for a function. You can add it all up for all the functions in a class. You can add it up for all the classes in a file if your language allows you to do that. You can add it up for all the files in a directory that comprise a module. You can take all the modules that make some larger component and do complexity at that scale, and you can do it for a whole product and come out with a number. And that number will be about 0.2, because every fifth line in your entire program is an if statement, right? It will be, it might be a little above or a little below. And what I found interesting is to build a map of complexity density across a large code base. So this square, in fact, it is a rectangle, but it is also a square, is a tree map. And the area of this square is about 2 million lines of code, right? So do people know what tree maps are? Not everybody is nodding, so I'll explain it. So a tree map is essentially a recursive subdivision of space, of this square, of 2D space, according to some hierarchy that you have elsewhere, like a file system directory hierarchy full of source code, right? So the first level of divisions, which on this tree map are vertical, like this broad vertical stripe here, that's one top-level package or directory or component in the system. And then within this big vertical stripe here, we have 4 or 5 horizontal stripes, and each one of those is a second-level directory or package in this system. And the area of each rectangle is proportional to the amount of code, measured in lines of code, in that package, recursively down to the leaves. And the color here is a function of complexity density. So the dark blue is very complex, and the white is very low complexity. And you can see that it's heterogeneous. Different parts of the system have different complexity densities. So what does that mean? That means the number of if statements per line of code is different in different parts of this system. And it doesn't vary hugely, but sometimes it's one if statement every 3 lines of code, and sometimes it's one if statement every 6 lines of code. So this actually tells you something about coding style in different parts of the system. Some of these people understand how to use polymorphism, right, and avoid having if statements because all of their branches are done by essentially polymorphic function dispatch, virtual functions if you come from a C++ background. Right, so some people are building their system in different ways to other systems, and you can see that at this level. Now, I don't know the details, but you can go and then begin to talk to people or begin to look at the code yourself and find out the reasons for some of these things. But when you come in, especially if you come in afresh to a very large system of 2 million lines of code, where the hell do you start? Well, you start with the architecture documentation. Oh, right. Really? So you could read all the code. Do you have any idea how long it takes to read 2 million lines of code? It takes a long, long time. And these systems can be deeply impenetrable if they are old. And what's interesting is they are old, but it's still important that we work on them. So that means they're valuable, right? We tend to look down our noses at legacy code in this industry, and legacy is a kind of dirty word, right? Well, actually, legacy, if you get a legacy from your ancestors when they pop their clogs, right, that's a valuable thing, right? I mean, you inherit a house or some gold bullion or whatever they leave you. And that's a valuable thing, in monetary terms at least. And legacy can be a positive thing, right? And the reason we are interested in legacy systems is because these systems have value. If they don't have value, we stop using them. So it's interesting to be able to navigate around these things. And what's perhaps even more interesting is that if you have really good records, like you have records, or like you have some sort of connection between your defect tracker and your source control system, and you've had that connection for 12 years, so that for every defect that was fixed in the system, you know which lines of code were changed to fix it, and then refix it, and then refix it 5 years later. If you can follow those relations between your source control and your and your defect tracker, you can then begin to locate defects in space, in code space. And so then you can begin to ask questions about, well, does defect density over time correlate with complexity density? And yes, it does. There's a strong relationship up here. Correlation coefficient of 0.6, that is by definition a strong correlation. It's not a very strong correlation, but it's a strong correlation. So complicated, high complexity density code has more defects in it over time. So that's a motivation for avoiding complexity, not just readability, it just is less likely to be right. And because with really good records you can locate every defect in the code, that means you can plot every defect on a tree map. So this is a tree map plot, exactly the same code base we were looking at, actually, yes, exactly the same code base we were looking at previously, where I've plotted the last 22,000 defects, right? That sounds a lot, but in 20 years, you know, it's not that many, 2 million lines of code. You can plot every defect on your tree map, which is kind of a fun thing to do, because then you can see which parts of the system all the bugs are in. And you can also see how people fix bugs, which is kind of interesting. So there's obviously something going on up here, right? What I didn't tell you about this tree map is that because it's based on the directory structure that the source code is in, it's sorted alphabetically this way, right? So the directory beginning with A is over here, and the top level directory beginning with Z is over here, right? So X is about here, right? Oh, sorry, W is about here, and it doesn't matter what the W stands for. But within the W column, the next level down, X is about here in the alphabet, because it's A to Z up the column, and X is about here. This is a hand-rolled XML parser, right? For some really horrible XML format that somebody decided to write in C++, right? And it's disgusting, and it will never, ever work. So you get these maintenance hotspots which just consume vast amounts of energy. Now, when I build tools to do these kind of things, you can make interactive versions, right? So when you hover your mouse over these things, it tells you exactly which function you're looking at, or which class, or whatever. So you can make these things more interactive in real life than I can show you on the slides here. Turns out that in this code base, there was a top-level directory called actions, which is a kind of euphemism for user interface, right? So A is at the bottom of the alphabet. So you can see there's a very high density of defect fixes in here. Lots of defects are just plastered over in the UI. There's some deeper problem in the system, and people fix it at a higher level. But of course, that doesn't really fix it. That plasters over it. So the fix doesn't really work. So then somebody has to come and do another fix, and another fix. And so you get this band of high complexity here. This really good code here is actually not really good. It's just older than my data goes. So you have to be careful how you interpret these things. My defect record goes back 12 years or something, and this code is 15 years old. You know, so you do have to be careful. It allows you to find parts of the system which are either fabulous, and you need to go and find out who wrote that, right, and get them to write everything else, or they're just not used. There are no defects in it because this code is never executed. I think in this case it was never executed. You can delete it, but then your diagram's less good. So and the correlations aren't necessarily what you expect. So I think you really have to use these, you know, because of things like this. Yeah, we have very complex code with no defects in it because it's not used. It doesn't matter that it's really complex. We don't need it. We're going to delete it, right? So use these things as drivers for conversations with the people who hopefully you still work with, but they've probably left, as you know if you came to my talk yesterday. Use these things as conversation starters. You know, don't set up some automated system that starts emailing people when their code complexity goes over some arbitrary threshold you've thought up. That is not the right approach. The right approach is to use these things as essentially a kind of surveillance tool, which you can then use to go and start a conversation with somebody who is now responsible for that part of the system. Don't forget the human element in this. And I think this is where people really slip up with a lot of metrics things, or why metrics come in for a bad name. It's because people plug metrics into completely automated systems which don't take any account of the human element. And what we do is a very human activity. It's a social activity, building software. Okay. Let's move on, have a bit more fun with metrics. This is a tweet by me from, when was it, earlier this year. I was sitting on the train on my daily commute into Oslo. I live a little way outside Oslo. And I commute in every day. And I could see this person on the train, about 5 rows of seats in front of me, working on some code. And I have no idea what language it was in. I could maybe guess. But I could just tell it was awful code from that far away. Right? How do you know that? Well, this is the best thing on the internet. This is not the code I saw on the train, but it's allegedly real code. So the point is that you can't read the actual code, but you know that that is bad code, even right at the back of the room, right? Because of the shape of the code.
What's the complexity?
Right? Well, the complexity of that is just off the scale. But it's just ludicrous, right? So you don't actually need to be able to read the code. You just need to be able to look at the general shape of the code to be able to say something about how complex it is. So I was inspired by this moment. I thought, hang on, this is the world's simplest metric, right? We can take some code. This is actually part of the source code of Git, I think. It is. I just downloaded part of Git. And I chose Git because it's written in C, and I know people in C write long functions and don't do unit testing. So, and all you have to do is tot up the area to the left of the code, right? And this is quite a nice metric because people with good coding practices don't have any spaces on their blank lines. So blank lines get ignored, right? Because blank line scores 0. So you just tot up all the space to the left. And we say, well, this function has 357 spaces in it. This metric I have called white space integrated over lines of text. Right? We can normalize 357 by the standard indent in this code, which is 4-space indent, right? So we can measure it in number of indents rather than number of spaces. The quarter here is because there's a comment here with a 1-space indent. That's fine. And so the wilt measure is the simplest possible code metric. And you can measure wilt in my case, 3 lines of Python, right, is all it takes to integrate leading white space. And what's great about wilt is it's really fast to compute. You can compute wilt over 2 million lines of code in 12 seconds, right? To do cyclomatic complexity over 2 million lines of code, I know takes 12 minutes because we used to do it on every commit, right? And that really slows down the commits before, the commits then are stalled in the pipeline. Whereas you can measure this really quickly. And it turns out that it's a fabulous proxy for this much more complicated measure, right? This is the correlation of complexity density, this quite complex statistic, with wilt, right? And you can see this really nice trend straight through the middle here, right? So actually, although it's really nice to understand cyclomatic complexity density, frankly, I don't think you need to measure it. If you're working in a language that uses indentation to indicate structuring, just measure the leading white space, integrate it up, and give you a score. Super, super simple. Anybody can do it. That's the only completely original part of this talk. Let's move on. Pay attention to the time here. And look at structural complexity at the module level. So how does this happen? We have these beautiful designs that architects draw, maybe just sketches, maybe somebody's made the effort to turn it into a nice diagram, maybe someone's even made a fabulous UML model. And we start out with this, and inevitably we end up with something that looks like this. Right? Well, not inevitably, but all too often we end up with something that looks like this. Again, these are real software architecture diagrams. This is real dependency data from the same system, right? So what we do does not in any way match up to what we intend to do. So why is that? Or how can we characterize that? So a couple of metrics I want to draw to your attention are coupling metrics. How are things connected to each other? And there are two words here, afferent and efferent coupling, which are impossible to remember which is which, right? And the way to remember is afferent begins with A, like arrives, and efferent begins with E, like exits, right? Which all makes sense if you know the Latin behind it. And the ferent bit is related to the word ferry in English, which is to carry or to move, right? So afferent means carrying into, and efferent means carrying away. So you can think of, we have some simple system here. We have a supplier class, a customer class, and an account class, right? And we can see, apologies if you can't read the code, but the supplier class is using the customer class. The customer class owns an account, and in here we have a method called recover payment, where we have chained methods. We do, what do? We do customer.getAccount.withdraw funds, right? Think about what that means and why that code is really not wise. I mean, it's not wise because supplier now depends on customer and account in this diagram rather than just depending on customer. But if you physically think about what this means, if you owe me some money, right, what I'm saying is go up to that person and saying, give me your wallet, right? You're going to give me your wallet, and I'm going to take money out of your wallet, and I'm going to give your wallet back to you. And you would never do that, right? You just wouldn't do that. If you owed me some money, I would come up to you and say, give me some money, right? And then you would go and dig around in your wallet to get the money, and then give me the money, right? Do you agree? Who here would give the person their wallet, right? Nobody, right? But you see this in code all the time. You get these chain method calls, and each extra chain on the method call is give me your wallet, basically, through these getters, right? And so this is where the thing about getters being bad is. That idea comes from. Getters are bad because getters are usually things like give me your wallet, right? And so because of this, even though the account doesn't really feature in here as a private member or anything, supplier depends on account because we do supplier, or we do customer get wallet or get account essentially. And so for each entity in here, we could give a score, which is the number of incoming dependencies and the number of outgoing dependencies. So the efferent coupling of supplier is 2 here, whereas customer, the afferent coupling is 1 and the efferent coupling is 1, etc. But if we refactor this and follow the good advice from the law of Demeter about not chaining our method calls, about not relating to the friends of our friends and only relating to our immediate friends in the object graph, then we can refactor this so we ask the customer to make a payment. And the customer makes a payment, right? And now the coupling is much, much lower. The total coupling of the system has gone down. So this is also an interesting metric. And I don't do it in this talk, but you can also aggregate these things over larger scales of code and look at the ratio of efferent coupling to afferent coupling. And Uncle Bob has some stuff from 10 years ago about these statistics and how to use them and interpret them in your system. They're quite interesting to give you an indication of the degree of coupling in your code. Perhaps an easier way is to use a thing called dependency structure matrix. This was invented, I think, in the 1950s in the nuclear safety industry. And so what we do is we take all of our modules and we sort all of our modules topologically into one linear list in the order that we think they should depend on each other with no cycles. And we plot each module along both axes. So the names of the modules on these axes are the same. So there's no hierarchy here because we've topologically sorted the dependency graph or the ideal dependency graph and flattened it into a single list. And then we have using modules here. So here is a module that is using the corresponding modules on this axis according to the cells in the matrix. And if there are no cycles in the dependency graph, then you get a lower triangular matrix in here. And it's interesting again because you can see, and this is essentially a visualization of efferent coupling to afferent coupling. And so we can see here that these modules are highly efferently coupled. they are using lots of other modules. So these two modules here are using loads and loads of other modules, whereas this module here is used by lots of other modules. So it's a very, very concise way of getting an overview of your system and seeing where some of the problem spots are. Let's look at how some of these things evolve over time. You see the date at the top, 2001. This animation runs for a little while. Area is proportional to source code size. We start off with 800,000 lines of code. The system's going to grow to about 2.2 million lines of code over 10 years. There's about 50 people working on this system. What's interesting is that, wow, where did that come from? Whoa, where did that come from? This is what happens when you get code written by contractors and you have no control. You have no control over the quality of what they're writing, right? And they write some enormous body of code. But what's also interesting is that the color of the individual rectangles is not changing. You never see a rectangle. You know, it starts out with a nice shade of pink, and it stays that same shade of pink pretty much throughout the course of its history. None of these modules are getting significantly simpler, but also none of them are getting significantly more complex. Why is that? Well, it's because people write code in the style of the code that they are modifying. Right? If you're working in some beautiful object-oriented code where everything is done by polymorphism, it's really easy for you to carry on playing the same game. Right? If you're working in code where there's no polymorphism and everything is done by switch on type, what are you going to do? You're going to switch on type, because otherwise you have to refactor the whole module before you can begin behaving properly. Right? So what I found is that the complexity of modules is baked in very early in their life cycle in the style of whoever started them, when they were tiny, right? And that just persists forever. Yeah?
Depend on language? Some languages have
That's a good question. This is a C++ code base with pretty awful tool support, as you well know. And actually, the whole diagram does get a bit paler in the last 3 years, where people were, well, essentially after people read the refactoring book and started doing refactoring the hard way, as you would do in C++ without tool support, they just realized it was useful and important. Yeah. So I would expect tools to make a big difference to this. But even so, some of the bigger refactorings are quite a significant effort. You know, I mean, extract method is super cheap, right? We can all do that with our keyboard shortcut or rename. But some of the bigger refactorings, you know, replace conditional with polymorphism, right? That can be a couple of days' work or more to do those things. So yeah, we started out with 800,000 lines of code. Things got really bad at one point when the contractors delivered some stuff. That got thrown away because it was no longer needed, fortunately. The business case for that went away, that functionality. But the overall complexity density of the system has barely changed over 10 years and over a vast quantity of code. It's basically the same. And I don't read too much into these numbers. I think you would have to look at these numbers per system, right? And obviously doing that will itself take language and all the other factors into account for that system. Other really simple metric is size. We have two charts here, time on the horizontal axis. This is size of the code base, just total lines of code. So this is 2,184,000 and something lines of code. Yeah? And this is complexity. And you can see they're very highly correlated. Right? Again, you probably don't need to measure complexity. You can just measure size. Right? And you can see these periods where the thing is just kind of quietly growing. You know, I don't get too excited about those. I'm very pleased by these. People are deleting stuff. Fantastic. Great. That's less liability, really. But, you know, when people start doing things like this, what's going on there? Is that just someone delivering a big merge from another branch? Maybe. Maybe that's entirely normal. Maybe there's something more. We'll come back to these charts later in the talk and talk about them. Let's look at dependencies over time. You can animate all of these things over time, right? Here's a dependency structure matrix. I think we do this over 3 or 4 years. Same system. This is through a refactoring project. So refactoring projects do exist, right? You can make them happen. Look at the number of modules going up as we decompose the system, right? Look at the density of the structure matrix going down, right? A lot of this was very blue before, dark blue. Now it's quite sparse. That's really good. Coupling in the system is going down. So what you're seeing is a refactoring where we went from, 30 modules to 150 modules, right? And of course, there's a hierarchy to these modules, which you can't see in this diagram. And that was happening because each module, these very large components, were being broken up, and they were being broken up again. And you might think this is a colossal effort, but it's not. This is what 3 people can do in 6 months. Yeah? And if you're working on a team with 30 people or 100 people, you can find 3 people to do that. Sure you can. And the benefits are enormous. They are huge. And in the process, you understand how the system you have works as well. If you're really diligent, you can document it as you go, right? So large-scale refactorings can work. I know it's almost impossible to get support or time or money to do them, but they can be effective, right? So don't give up. Don't give up. And this is in really, truly awful code, some of this. And now it's much, much better code. You know, and this isn't all just extract method and things like that. It's very well thought out, planned refactorings. There's a lot of moving code between modules to make the modules cohesive. So all the stuff in one module has one set of responsibilities that is closely related, right? That takes a lot of effort and design and planning to do that. Actually, doing the refactorings is relatively straightforward. Knowing which refactorings to do is where a lot of the conceptual effort goes in. Okay, let's look at causes. I want to do away with this one quickly. I think it's completely true. I've always worked in product companies, and the biggest primary cause of complexity is customers, essentially, asking for things, and then the company that sells the software actually listening to the customers, uncritically. Right? It's an enormous cause of complexity. I'm not going to talk about it any further. But there are several basic causes, I think. There's ignorance, not knowing the techniques necessary to avoid complications. There's a lot of that about. People don't know the techniques. There's convenience, which is knowingly doing the easy thing rather than the right thing. I had to fix some code in a hurry earlier this week on my way to this conference. Right? And I knowingly did the wrong thing, right? I hope I have time next week to atone for my sins, right? But we've all done it. The circumstance, which is being unable to do the right thing because of the situation you're in, which could be a social or management situation, or it could be a technical situation. And then there's the tragedy, the tragic situation, which I'll talk about a bit at the end. We'll try to get through these quickly. Okay, what's this? Scrabble, right? Solid, thank you, solid. Who knows what all of these are? Who knows what any of them are, right? Solid principles, hands up if you know what the solid principles are. Nearly everybody, fantastic, right? Single responsibility principle, open-close principle, Liskov substitution principle, interface segregation principle, and dependency inversion principle, right? I made this photograph myself from a Norwegian Scrabble board, which is actually impossible because Norwegian Scrabble sets come with 2 letter P's. So I had to Photoshop the other letter P's back into the thing. And this is why C is worth 10, because Norwegians don't use the letter C. So. And Norwegian Scrabble doesn't even come with the letter Q. But they have 3 other letters to make up for it. But you know, the fact is, we hire people who don't necessarily know all this stuff. And those people can cause a lot of damage, not through malice, but just because they don't know, right? And the people who do know have to help them learn this stuff on the job somehow. I think it's important to know when not to apply principles. Right? We have some module A which uses module B. The people working on module B see some really shiny thing that they wish was in their module, right? In the other module. But they've heard of the dry principle, right? Don't repeat yourself. So they depend on it, right? They use it. So we'll just go and get it. We can just call it. It's in the other module. So now we have a cyclic dependency between two modules, right? Is that more or less evil than copying the 5 lines of code they wanted to use? I would argue that copy-paste is the lesser of two evils here. Everything in software architecture is about trade-offs. Understand the trade-offs. And I think our biggest fault as a community is that we're so zealous and religious about all of these things. And somebody puts up a blog post, and we all interpret that as the truth, which is just immutable and is always true in every circumstance. And that's almost never the case. All of these things require judgment and thinking to know when to apply them. Sometimes copying 5 lines of code is the right thing to do. It might not be a very important 5 lines of code. Usually it isn't. Convenience, knowingly doing the easy thing rather than the right thing. What do I have here? Right, this is the switch versus polymorphism example. I mean, you have some disgusting class hierarchy that should never have existed in the first place. And your job today is to add another class to this system, right? So what do? You add another class to the system, and then you go and modify the 35 switch statements which dispatch on the type, right? People do this all the time. It's wrong. We know it's wrong. But they do it because it's convenient to do that. It's really easy to search for these switch statements because they're all switching on the same enumeration, right? So it's easy to find those. You can just grep through your code, find them. It's going to take you 10 minutes to modify 30 switch statements. Easy peasy. Rewriting the whole thing to be polymorphic and use virtual dispatch is going to take you 2 weeks, right? So there's a trade-off there again. But ultimately, these things all increase complexity. And the size of functions is another good example. Nobody writes 1,600 line functions, right? But many of us have probably added 5 lines to a function that was already getting a little bit too long, right? Haven't we? Nobody sets out to write these things from scratch, but we are all been guilty of an increment in the wrong direction. And that is the moment that we should have refactored. But it's like, well, it's not really our function, is it? Someone else will refactor it. Well, no, they won't. This is the size of a particular function over 10 years, right? Starts off at, 900 lines of code. The big jump here, someone adds 400 lines of code, stable for another 5 years, then another 500 lines of code comes in. Right? These are probably merges coming in from other branches, so it's probably not somebody sitting down and writing 500 lines of code. Right? But somebody in those other branches over the course of a year added 5 lines, 10 lines, 15 lines to these things, and they grow. There are occasional efforts to improve the situation, but they're not really very effective in the grand scheme of things. Circumstance. Those of you who came to my talk yesterday will be familiar with this slide. Agile adoption is hard, right? And because it's hard to do real agile, I think. And many teams end up doing what I call nominal agile. You go to them and say, what are you doing? And they say, we're doing agile, right? But then you actually look at what they're doing, and they're not really doing agile. They're doing whatever they were doing before in 2-week chunks, right? I mean, that's basically what a lot of teams are doing. We have a planning meeting, we have a backlog, this guy's the scrum master. We're doing agile. Well, no, probably you're not. You're probably not doing any of the agile engineering practices. I use the word engineering. Tom is still not here. That's okay. So, you have to be, it's really hard to do this well. And I don't think many teams are. And what happens in here is that things can get really bad, I think. Because everything's on really short time scales. Nobody's thinking ahead. It's all about just getting to the end of the next sprint. Right? And all the things that mitigate the short-termism, like the refactoring you would do in real agile, aren't happening. You're just compressing the deadline down. So everything's in just a rush now. So I think a lot of teams are here and claim to be doing agile. This is why I use this word agileness rather than the word agility. Here. Agileness is my word for how hard you're trying to be agile, right? Rather than agility, which is how nimble you actually are. And of course, some environments make doing the right thing really hard. If you're in here, and you're faced with this, it's really hard to do the right thing. Circumstances set against you. What is that black hole? That is the dependency graph for a different system, right? After my fairly substantial workstation had spent 5 hours or something trying to find the most elegant way to lay out the nodes in this graph so that I could actually see what the hell was going on, right? It's a really tough optimization problem, and there is no solution, except those of you near the front can probably see the fact this is made of millions of lines, right? This is a real system. It's really hard when you can't even visualize the thing. Right? I mean, what do you do now? You just have to start filtering, actually. I think if you get these things into a graph database or something and then begin querying on parts of the system and filtering bits of it away, you can probably learn a lot. And of course, that makes other problems arise. When I've worked on systems like this in architecture roles, one of the most frequently asked questions I got was, where do I put this new thing you want me to build? And in that situation, honestly, a lot of the times, I didn't really know, right? Because none of the existing pieces have nice, clear responsibilities. Right? So what do? We make another module. Right? And that's probably OK, but that module necessarily ends up connected to 50 other modules in order to do what it needs to do. It's really hard to break out of this. So Conway's law. Yesterday I said, who knows about Conway's law? And hardly anybody put their hands up. But that was yesterday, and I told you about Conway's law. So who knows about Conway's law? Whoa, great. You've all learned something in the last couple of days. So I don't need to explain it, really. Any organization that designs a system will produce a design whose structure is a copy of the organization structure. Right? So if your organization is set up wrong for the kind of system you're building, that's circumstantial difficulty. And if you don't have any influence over changing that organization, it's very, very difficult to do the right thing. Which is why I think people in senior software architecture roles, or any kind of senior development role, need to have influence and be able to talk to the people about how things are organized. It's very, very important. It's probably more important than anything else, actually. Let's check the time. OK, the tragedy of the commons. I have a whole other talk about the tragedy of the commons in software development, but we'll just do a brief version now. And this is about the unawareness of the global impact of locally optimal decisions. And it's a trap that we don't just fall into software, we fall into it with all kinds of things. So I'm going to explain the tragedy of the commons with respect to software. So I put this graph up yesterday as well, but who was in my talk yesterday? Nearly everybody. OK, for those of you who weren't, we'll do the same exercise again. It's fun anyway, isn't it? OK, who has changed project or company at any point within the last 32 years? Right? No real oldies here. 16, keep your hands up, everybody. 16 years? A few hands going down. 8 years? A few more. 4? Oh, lots of hands going down. 2? Okay. 1. Right. You can put your hands down now. So about half the people in the room had changed project within the last 4 years, right? Now, if you look at there is actually some published literature on this. The actual number is that the half-life of software developers in software companies is about 3.1 years, right? So every 3.1 years, half of your colleagues are replaced by new colleagues, right? Does that sound about right? Sounds plausible, doesn't it? So it's interesting to compare that to the lifetime of other entities in software systems. Applications, and line of business enterprise applications last 6.2 years. CEOs of companies they don't last 6.8 years, but half of them are replaced every 6.8 years. Sounds about right, doesn't it? You know, you work for a company for a few years, you think about how often your CEO is recycled. Lines of code in code bases I've worked on and other code bases I haven't worked on last 13 years. You don't have to have a 13-year history to do these things out, because you can do math, right? You can figure it out. FTSE 100 companies, half of them change every 22 years. That's quite quick. Classes in systems, 37 years. People don't remove stuff, they add it. Software accretes. That's the primary mode of software development, is just accretion, right? It just grows. We saw some animations of that earlier. It just accretes and grows. People aren't removing stuff. And so the half-life of classes is really long. It's 37 years in what I've worked with. And the larger the entity you deal with, the longer the half-life. So modules, for some definition of module that makes sense when I did this, 58 years. That's older than nearly everybody in the room, probably. Really long time. So what's the problem here, right? Is it the code, or is it the developers leaving every 3 years? And why are we leaving? Are we escaping the creations we have just built? Who's ever done that? Of course you have. So I don't think we really have sustainable development. I put this up yesterday as well. This is the definition of sustainable development from economics. But I think it's a beautiful definition because it applies wonderfully to software. If you think, rather than development of emerging economies or something like that, we think about software development, this definition is great. Provision meets ongoing needs whilst preserving the supporting environment. That's exactly what we want to do. We want to add features to systems. We want to deliver value without screwing up the systems that enable us to do that. Sustainable development. So the tragedy of the commons was an idea which we'll come on to now, which affects, it's an idea that's been around for a long time, and it affects things that are shared between groups of people, like the climate. This is a journal article about the climate. This is a science article about the climate. Fisheries is perhaps the canonical example of the tragedy of the commons. Fisheries are shared. Fish in the sea aren't owned by anybody. Anybody can go out and catch them. Well, subject to some regulation where people are aware of this problem. So the tragedy of the commons is an effect that occurs where you have any shared resource. And the guy behind the idea was a man called Garrett Hardin, he was actually writing essentially a game theory paper about thermonuclear war, I think in 1968. Yes, The Tragedy of the Commons in Science magazine. Well worth a read. It's a very short article, it's very readable, well worth looking at. And he basically said that resources held for common use by all will ultimately be destroyed. That's a pretty final statement, isn't it? There's no get out there. And he believed this so much, eventually he and his wife committed suicide. So it's a very interesting paper, and it's frankly, I think nearly all of it is still held to be true today in terms of how systems involving people work. So let's illustrate it with a commons. Hopefully many of you don't see this particular Windows XP common these days, but there you go. Who still sees this common? Wow, a few people. Oh well. And on this common, we're going to have two farmers. And this farmer is going to put a sheep on the common. He owns the sheep, right? That's his sheep. And the sheep is going to eat some grass on the common, thereby degrading the quality of the common, right? So the sheep has one positive unit of utility to the guy who owns the sheep, and it causes one negative unit of utility to the shared resource, which is the common, right? But he entirely owns the sheep, but the degradation is shared with the other farmer, right? So he only gets a half share of the degradation. So the total utility is +1 minus a half. So it's plus a half to him. And then she's going to put a sheep on, and the same happens to her. Her sheep also degrades the common. She gets a total utility of +half. Now, because his utility is a +half and her utility is a +half, because they're both positive, they both have an incentive to add another sheep, right? So he adds another sheep. She adds another sheep. And their positive utility of each sheep is still +1/2, because the negative effect is shared, whereas the positive effect goes entirely to them. And again, and again. And we get this runaway effect. I have to be careful with my animations here. So we get into a situation where essentially are both incentivized to keep adding sheep to the system, but the effect is that they get all the positive benefit of additional sheep, but eventually the common degrades, right? Because the sheep eat all the grass. There we go. I think he's the last one. No. There we go. Right, and eventually the common is destroyed. Right? Ultimately, the shared resource is destroyed. We have some dead sheep. There are no farmers because it can't support them. And I'm running a little bit short of time, so I'm going to skip over this. National parks, they're closed anyway. Don't worry about it. Yeah, quickly, museums in London, right? I wanted to take my kids, brought them from Norway to go to the Natural History Museum. Wonderful educational experience, or so I thought, right? When I got there, it was like this. Nobody was being educated. Nobody was enjoying themselves. It was just horrific. It's a really horrible experience, right? This is a tragedy of the commons, and it's caused because access to the museum is free, right? That doesn't mean you should have to pay. You could have a limited number of free tickets per day and avoid this problem. You know, you can have creative solutions to these things. There are lots of potential things. Anything that's shared, essentially, the radio spectrum, the internet, we all heard of net neutrality, right? I would argue that software systems suffer from this effect too. We all share the software system we work in and rely on it as a resource on which we use to deliver value, to deliver features. But because it's shared, anything we do degrades it. So how does this happen? Well, it happens one dependency at a time, right? Every dependency you add as a programmer into the system, in whatever language you're using, is plus one utility unit to you right now, and minus a half utility unit, or whatever the number is, some negative number, to everybody else who uses that system ever, right? It's much easier to add dependencies than it is to remove them. And that effect of positive utility entirely to you now and negative utility shared is all you need for tragedy of the commons to occur. Everything else will just happen, right? It's just nature. And so every import or include or using statement is another sheep on the common, effectively, that degrades the whole system. So I think you have to be really careful with how dependencies are introduced. And the problem, of course, is that this is a moral hazard. This is a word that was thrown around back in 2008 quite a lot, in this part of the world, certainly. And a moral hazard is essentially any situation where one person makes a decision about how much risk to take, but somebody else bears the cost if things go badly. Right? So you, as a developer, take the decision to add a dependency, another using statement, right? But everybody else bears the cost of that if you made a poor decision. So we have this tragic cycle, I think, of short tenure of developers, because we're all leaving our jobs every 3 years or 4 years. This creates a moral hazard, because we're not going to be there, right, when it all really goes wrong and the complexity's gone off the scale. That's the tragedy. Systems turn out really bad, which causes us to leave and escape the systems we've created. And I think this is a very nice, I would argue this is a very nice example of the tragedy of the commons in action, and illustrates why systems degrade progressively, and Garrett Hardin would say inevitably, right? I think the only control we have is how quickly they decline. Let's finish, maybe even on time, if we're quick, on controlling complexity. I think a very important thing is to be able to talk the language of the people you're dealing with. Software architecture role, you should be talking to all these other people, right? Not just the developers, but the business owners, the customers, the management, the users, really. Testers, if you have them as a separate function, marketing, if you're in a product business. And all these people want different things, right? Don't go and talk to them about complexity, right? Don't say, well, the average ratio of afferent coupling to efferent coupling is 3.142, right? That may be true. It is not useful to them, right? Don't do that. You know, go and talk to them about maintainability, the qualities they care about. Modifiability, right? All these things they want you to do to the system require it to be modifiable. That requires it to be maintainable. That requires it to have low complexity so you can do these things. So shift abstraction level when you're having the conversation, depending on who you're talking to. It's very, very important to use the right words to the right people, even if in your mind they're kind of synonymous. Different people will hear different things. Test-driven development. We've got some TDD superstars in the room here, so I hope I say something vaguely intelligent about this. But testable code tends to display other good qualities. My colleague Austin Bingham had a talk about this the other day. Testable code has low cyclomatic complexity, loose coupling, high cohesiveness, all of these nice qualities which tend towards low complexity. So even though I'm not sure low complexity in a kind of metric sense, as I've described it earlier, is an explicit goal of TDD, but it's a very good side effect of TDD. And I think if you're doing TDD well, lots of other things will happen. So, of course, TDD, I would argue, mostly helps at a fairly local scale in your code. It's going to help you with coupling between classes and the complexity of methods, but it's not going to tell you that you should have a microservice-oriented architecture, right? I don't think you can TDD your way to that from a monolith, necessarily. And the only useful way to prove usability is to actually have tests. Do some strategic design. I think this is a word that Tom Gilb has also been using as a synonym for architecture, and I really like it because it gives you a sense of the longer-term thinking, something else I talked a lot about in my talk yesterday. I think the major difference between, I said yesterday that both TDD and software architecture are essentially concerned with the same things on very different timescales, right? We do TDD, we go through the design cycle every 5 minutes or every half an hour. For software architecture, the timescales are weeks and months and years. And nothing in Agile prevents you from doing whatever it said there. Trust me. What did it say there? Okay, these are the same diagram. This is a sketch in the vein of a Simon Brown-inspired sketch, and this is the beautiful diagram, right? And you don't have to invest in the beautiful diagram drawn in Visio or whatever, or the model behind it. It doesn't necessarily deliver any more value than a sketch you can draw in 10 minutes, right? And nothing in Agile says, don't draw sketches of things that take 10 minutes. Nothing tells you not to do that. Agile probably has a firmer opinion about not investing 3 weeks in Visio, right? But sometimes you need to spend 3 weeks in Visio because you need to talk to a really important stakeholder who is, frankly, not going to be convinced you know what you're doing if you put some scrappy sketch in front of them. So again, change the language, change the style depending on who you're talking to. Your developers are quite happy with a sketch. Refactorings reduce complexity, right? Back to cyclomatic complexity we talked about at the beginning. If you take, so we're switching on the type of swallow or bird, right? We have a European swallow, an African swallow, and a Norwegian blue parrot. And we're switching on the type of those birds, right? Which is not what we should do. We can do our replace conditional with polymorphism refactoring. We can have our nice hierarchy. And when you look at the complexity of the switch, it comes out at 7, because there are 4 exits from this switch, which really counts against you, because we're exiting from within each case here. Whereas the complexity of each branch of the switch when it's put into its own function is only 1. There's no branching. Right? So the total complexity of this is only 3, right? And 7. So this shows how the refactorings can show up in the metrics. And of course, when you aggregate these things over large amounts of code, you would hope that refactorings would make these aggregate numbers go down. I love this quote by the technical director of EVE Online. How many if statements does it take to add a feature? I think this is a really good question to ask of developers. If you were to do this, how many if statements would you have to write to do it? That immediately tells you something about the quality of at least the class level design in a system. It's a really nice question. There are lots of tools out there to help you. I tend to make my own tools for 2 reasons. One is I've worked in environments which don't have off-the-shelf tools. The other is if you make your own tools, you can explain to those tools things about your system that no off-the-shelf tool will know. Right? You might have specific conventions or rules in how you want your system to be laid out, how you want it to work, and being able to explain those conventions to your own tools or build them into your own tools is really very useful. Right? Whereas the off-the-shelf tools tend to be, well, just naturally less flexible and more generic in terms of the kind of things they can help you with. So Sonar, I guess mostly for the Java people, ndepend is a good tool that will do a lot of these things for you if you're on .NET. If you're not on either of these platforms, you're probably going to have to build something yourself. But it's not hard. You know, I showed you how to do a wilt metric in, 3 lines of Python. Super simple. Find out why. Use these things as conversation starters. Use them to go and find out why this person felt the need to write their own XML parser. It's a really good question to ask. You know, and it probably won't be because they're stupid, right? There'll probably be some deeper reason behind it. It may be because they're stupid, but there might be some deeper reason behind it that you should find out. Maybe they weren't allowed to buy whatever licenses they need for whatever tool they needed. Likewise, when you see a big jump in the complexity or just simply the size of some code, dig out that change. I just made this is just a simple web page I threw up that was continuously updated with the size of the code with every check-in. You could hover over it and it would give you the check-in comment. Why did this person called NR1, that's a contractor, which is why it's an obscure name rather than Bob or Janet, fix a bug, right, by adding 4,000 lines of code? Right? Why? It's a bug. Bug ID 30266, right? What do? I go and read bug ID 30266 and find out that it's some trivial thing. You know, we misspelled something in the UI. And, and then go and find out where the 4,000 lines of code ended up, and then go and talk to that guy and say, well, did you really need to do this? Or why did you do it? And maybe it's completely legitimate, and sometimes it is. And sometimes it's just a mistake, you know. They just committed the wrong thing, gave it the wrong comment, got confused. We've all done that, right? Maybe it's just innocuous and you can easily roll it back. Maybe it's really sinister, right? Just find out, right? Do not have an automatic system that fires this person, right? It'd be very easy to write an automatic system that just sent an email to HR, you know, minus 1 million points on next year's review. Right? Don't do that. Go and talk to them. That's your job. Go and talk to people as an architect. I mentioned this, actually I haven't mentioned this, encode design constraints into your build system, for example. Right? If you have local conventions or rules, or dependency rules in particular, if people violate those, make it so they can't build it. Stop them violating it. Right? Most build systems will build almost anything you throw at them eventually. Right? Whereas if you build your own conventions into these things and run them often enough, it might not be every commit, it might be too expensive, but it might be once a day. So the latency is short enough that you can go and track these things down. But build the rules into your systems and build custom tools to do that if you need to. Most build tools are pretty customizable and programmable. And I think as a software architect, you know, we say software architects should code. It can be awkward for software architects to get too involved in production code because, as Osharov was saying yesterday, architects become bottlenecks, right? And if architects commit to do something on the sprint and then spend the next 3 days in meetings with management about something else, then they fail to deliver their commitments in the sprint. A really good way of contributing to the overall good of a project is to get involved in these kind of things. There's still lots of useful coding you can do here that oils the wheels for the whole project, but also builds your own knowledge of the larger system as a whole and gets you into a situation where you talk to lots of people, maybe in lots of different teams as well, which is what you need to be doing. You could one of the solutions to to the tragedy of the commons is to tax the thing, right? Privatize it or you tax it. So you could make negative behavior more expensive, right? So maybe you do code review. Maybe you shouldn't treat all changes equally, right? If somebody just adds, prints a string to standard out, that's probably pretty innocuous, right? But if they add a using statement, that's still one statement, but that has a different cost on the overall complexity of the system. Maybe you could find those things and flag them for additional review, maybe by more people, maybe from a wider constituency. Maybe if you're depending on things, rather than having something reviewed by one other person in the team, maybe certain types of change you can probably automatically identify should be reviewed by more people from a wider constituency, right? This has two interesting effects. It makes those changes more likely to be right, but it also makes those changes more expensive for the developer to do. Right? You've taxed it, right? And taxation is one of the tools you can use to solve the tragedy of the commons. Perhaps I think it's probably quite a controversial idea, right? You're deliberately slowing people down. You're penalizing negative behavior, right? But you're doing it in quite a progressive way. It's a progressive tax, right? Software architecture is all about trade-offs, right? All of these things are about making the right decision at the right time, and very rarely is it completely obvious which is the right way to go. You're just going to have to decide whether you want the healthy apple or the fabulous chocolate cake. But you have to think about it carefully, because one of them is really good for you, and the other one is going to make your bum a little bit bigger. I'd like to end on a few quotes. I think this is fantastic. It's a message about consistency, right? You've all read it. I don't need to read it to you. But if you saw the heterogeneity in some of those larger systems earlier. If everybody is doing everything in a different way, it's very difficult to keep on top of that, right? I think you have to allow individual teams to innovate in order for them to be able to do things better, in order to be able to discover new ways of doing things. But at the same time, you have to moderate that with just being reasonable about how innovative you're allowed to be, right? And essentially, I think you can divide all the solutions into preventative and curative solutions. Preventative is things like architecture, design, organizing your organization appropriately, Conway's law, educating people. Right? There's no point educating them afterwards, right? You have to educate them before they're going to do whatever they're going to do. And things like TDD, I would argue, are very preventative measures. And then there's curative measures, things you can do afterwards, like monitoring, so you can follow up, talk to people. Refactoring, like the larger scale refactoring I showed, that's a curative measure. Things had gone badly wrong, and we substantially improved the state of things by working very hard on it, but with a relatively small number of people involved. And reviewing things, of course, is a curative thing. Melvin Conway, Conway's law, who made the remark about organizations and the structure of the systems those organizations build, said something else, and I think he even said it in the same paper, which is there's never enough time to do something right, but there's always enough time to do it over, to do it again. And I think that's very, very true. All of those refactorings we looked at earlier, those refactoring projects, that's rework, that's doing stuff again. It's costing a lot of money to do that. And finally, Alan Perlis, simplicity does not precede complexity, but follows it. Oh, not finally, one more quote. Garrett Hardin, Tragedy of the Commons, there is no technical solution. Right? This is that is the conclusion of his paper. Right? There is no technical solution. There are social solutions, right? You can modify people's behavior by taxing them or whatever, or educating them. But there is no technical solution. So you can throw technology at these problems to point you in the right direction, or to help you solve problems when you found them. But ultimately, you're just going to have to deal with people, right? People caused all of these problems. They didn't just arise out of nowhere. Right, I am done. Thank you very much. I've run over time. Thank you for staying for the extra 2 minutes, 55 seconds. I hope it was worth it.